Hello, my name is Viktor Sowinski-Mydlarz. I am a research fellow in machine learning at London Met Cybersecurity Center. In this presentation, I am going to talk about containerization of a neural network. Let us begin by explaining what a neural network is. It is a network of neurons similar to connections in an organic brain. Our model has three layers: input, output, and hidden one that does the calculations. More hidden layers means more complexity, but can result in overfitting. The data used for experiments come from public domain, namely a repository called netresec. We can analyze two formats, packet captures and comma-separated values, varying in size from 6 to 318 megabytes. And the samples include traffic from machines infected by Trojans, URSNIF, and TrickBot, and also examples of direct denial of service. Numerical data are packet numbers, the time and length of the packets, whilst categorical data are source and destination IP addresses, protocol use, and packet flags. Containerizing means wrapping an application with necessary libraries, dependencies, and config files needed to run effectively on different platforms. It is a method of virtualization where isolated apps run on a common OS kernel, and Docker is the most popular platform for containerization. There are a lot of benefits of containerization: better memory processing, storage management, disadvantages over conventional hosting, portability and independence, also reproducibility and simplifying DevOps approach. Container can execute on any platform with same operating system with no changes in code needed. Docker Compose is a tool for running multi-container Docker applications. It uses YAML for configuration. YAML acronym stands for YAML Ain't Markup Language. One Docker file defines the app's environment and it can be reproduced anywhere. The first out of 5 containers we are using is Airflow. Apache Airflow is a workflow automation and scheduling system for data pipelines. In our project, it serves as a user interface or dashboard for executing tasks. These tasks are called DAGs, or directed acyclic graphs, and these tasks use workers to execute Python code. Initial model DAG runs only once. It loads and preprocesses data. It constructs and feeds neural network model. Streaming DAG runs every 5 minutes and uses broker to take messages from the Kafka producer, which is the source. It stores these messages to a Kafka topic, which is the server stream. And finally, consumer, which is the destination, fetches messages from the topic. Updating DAG runs every hour and retrieves data from Kafka topic. It loads current module and evaluates the score. It also adjusts class weights for underrepresented data that should get more attention. It compares the scores of the models and saves the better model. And it finally sends the metrics or statistics to MLFlow interface. Postgres Container is an open-source object relational database management system. It uses its own procedural language, and it basically serves as metadata database for Airflow containers shown in previous slide. Apache Kafka is an open-source stream processing software platform. It publishes and subscribes to streams of records called topics. It stores streams of records in a fault-tolerant, durable way. It processes topics as they occur. Kafka's TCP protocol is language agnostic, so it works for any language. Zookeeper is another open-source Apache platform. It provides a centralized service for configuration information, naming, synchronization, and group services in distributed systems. It simplifies management and basically keeps track of Kafka streams and partitions. MLFlow is a set of APIs and user interfaces that can be used with any machine learning framework. It tracks experiments, packages code into reproducible runs, shares, and deploys models. The user interface is accessible from the web browser, same as Airflow interface. MLFlow allows to visualize, search, and compare runs. It shows the results of incremental learning, as you can see on the left side of the slide. Our code has been parameterized, meaning that the configuration is exported to a config file as opposed to being hard-coded. The first configuration is the baseline for generic state of the model before any threads. Next, 5 scenarios are modeled, namely ATM infected, cross-channel with pretexting, scareware and rogue, transfer with direct denial of service, update antivirus with spyware. The detection of threats is based on patterns of 3 elements, which are types of suspicious packets. Configuration files contain paths to components, the name of the packet capture file to read for initial model training, and filters on packet types. It also contains class weight settings, Kafka client name, IP address, port, Kafka topic used for streaming, number of classes in the model, initial model path, etc. Let us briefly talk about data streaming and incremental learning. Packets are streamed from the sensor server and analyzed in batches of 1000 every 5 minutes. They are ingested and appended to the data array in a loop. Every 1000 records, we commit the Kafka partition and set the last offset as the beginning of a new transmission so that streaming is sequential. The model is updated based on how it scores on the test set. If it outperforms the current version, it replaces the current version and metrics are sent to MLFlow dashboard. To summarize, we have trained the initial model, we streamed data, we adjusted class weights and compared scores of original and adjusted model, we replaced the model and archived it, and we send the metrics to MLFlow. In the MLFlow dashboard, we can see the number of samples that were used to update the model, the accuracy and loss of the model that is currently in place, and the updated model, the number of epochs and the batch size used, and whether or not a run led to the current version of the model being replaced. And that concludes the presentation. Thank you. Goodbye.